Welcome to the class of centrifugal pump, where I will discuss about the basics of centrifugal pump, its working, and how to draw velocity triangle for a centrifugal pump. This one is the basic layout of a centrifugal pump, where the main parts of centrifugal pumps are shown here. First one is volute casing, which is a casing where the area is continuously increasing towards the delivery side. There is an impeller. Impeller is nothing but a set of backward curved vanes which is mounted on a shaft, and this shaft is being driven by a motor. At the center of the impeller there is an opening known as impeller eye, and water is being sucked from the suction side through it, and then it is discharges to the casing. Here you can see the impeller as their backward curved vanes are present here. So when these vanes start rotating, or the impeller starts rotating in anti-clockwise direction, then these water particles experiences a centrifugal force, and because of this centrifugal force these water particles move in outward direction. So when it moves in outward direction, at the eye suction creates, and these water particles are being thrown in the casing, and because of the larger area at the delivery side, it loses its kinetic energy, and potential energy, that is pressure energy of the fluid, is getting increased here. Here you can see semi-open type impeller where there is one cover plate and the backward curved vanes are like this. So in case of shrouded type, this type of cover plates are mounted on both sides of these curved vanes, whereas in case of open type impeller there is no cover plate at all, there are only these curved vanes are there. Now we will see how to draw velocity triangle for a centrifugal pump. I have considered here one vane that is set at, and it's set here as in backward curved vanes. First one, how to draw here. So we can draw here. As we know, fluid must follow the boundary, so the relative velocity of the fluid must be tangent to this blade. So relative velocity we have to draw here tangent to this blade. Similarly, relative velocity at outlet must be tangent to the vane here. Then we can add the absolute velocity of the blade at outlet. So absolute velocity of the blade at outlet is nothing but r times omega, where omega is the angular speed of the impeller. So r2 at outlet, the speed will be r2 into omega, and r2 omega will have the direction that is in horizontal direction, in this direction. So we will have to add this speed of the vane at outlet in the relative velocity. Then factorial sum of relative velocity and outlet of the vane will give us the absolute velocity of water at outlet. Similarly, velocity at inlet. So velocity of vane at inlet will be nothing but r1 into omega, and r1 into omega must have the direction tangent to this wheel and in this direction here, and so this can be again added here, and factorial sum of these two will be nothing but absolute velocity of water at inlet. So see here, this one is the absolute velocity of water at outlet, and this one is the absolute velocity of water at inlet. And because, as we know, in centrifugal pump water is moving in radial direction at inlet, and that's why the component of VW1 must be equal to 0. That is alpha equal to 90 degree. And the component of absolute velocity is nothing but known as wheel velocity. So wheel velocity at outlet must be equal to VW2. That is nothing but VW2 is written as V2 into cos beta. Whereas theta and phi are nothing but vane angle at inlet and outlet. So this is the absolute velocity, and this one is the absolute velocity at outlet, whereas this one is the absolute velocity at inlet. Whereas the flow velocity can be written here as the vertical component, that is absolute, the component of absolute velocity in vertical direction here, or in the normal to the speed of the vane here. Similarly, if we see here the component of absolute velocity in the direction normal to the speed of the vane is 0 here. That's why VW1 is 0. So drawing velocity triangle for a centrifugal pump is very easy. Very easily we can it, and as far as work done per second is concerned, this one is very simply we can write here as rho q VW2 U2 minus VW1 U1. Work done per second per Newton of water, that is simply work done per second is divided by weight of water flowing per second, and weight of water flowing per second is nothing but m dot into g, that is rho q g. So rho g will get cancelled out. We can get here 1 by g VW2 U2 minus VW1 U1. This one is also known as Euler's head. So here we can see how it's easy to draw velocity triangle for a centrifugal pump. Again I am repeating. First of all, draw relative velocity which must be tangent to the vane. That is here in this direction, because the centrifugal pump is an outward flow machine. So this must be in outward direction. Here it must be in outward direction. So this is relative velocity that is tangent to the vane. Then in this relative velocity, add the velocity of the vane at this point, that is U2. Similarly, add the velocity of the vane here, that is U1. It will give you the absolute velocity at outlet as well as absolute velocity at inlet. So this one is the vane angle at outlet, this one is vane angle at the vane angle at inlet, this one is the vane angle at outlet, and this one is the beta. So it's very simple to draw velocity triangle. So thank you for joining me in this lecture. In next class I will discuss some problems on centrifugal pump. Thank you.